Okay, so happy asynchronous day. So we've talked about how to find the limit by looking at a graph. So that's what this warm-up is for on the front. You're given this graph. Remember that when you find a limit, when you just have a graph, that requires a left-hand limit and a right-hand limit. And if they agree, that is your limit. If they do not agree, then the limit does not exist. So for the first one, I just noticed it says BB. Obviously, this is the first one. So you would do the left-hand limit is x approaches 0 from the left of f of x. So if I'm approaching 0 from the left, I'm going to be right here. And when I get to 0 coming from the left, the height of the function is 0. When I'm approaching 0 from the right of the function, I'm on this path, and as I get to 0, the height is also 0. Therefore, and you can use this already printed limit statement as your overall limit statement. All right, for the limit as x approaches 1, again, that's going to require a limit as x approaches 1 from the left. So if I'm approaching 1 from the left, I'm approaching from this path, and when I get to 1, I have a height of 2. It does not matter, there's an open dot there. The limit as x approaches 1 from the right of this function. If I'm approaching 1 from the right, I'm on this path, and when I get there, that has a height of 1. Since the left-hand limit does not equal the right-hand limit, the limit does not exist. Right? The limit as x approaches 2. Limit as x approaches 2 from the left. So approaching 2 from the left, I'm on this path. The dot is not going to factor into limits. We'll deal with the dot when we have continuity. So this is the path to get to x equals 2 from the left, and when I get to 2, the function has a height of 1. The limit as x approaches 2 from the right of the function, I'm just over here taking this path to get to x equals 2. That also has a height of 1. Since the left-hand limit agrees with the right-hand limit, the limit as x approaches 2 for this function is 1. X approaches negative 1. So if we start with the left-hand limit as x approaches negative 1, you can see there's no path that we can see to get to x equals negative 1 from the left. So the left-hand limit does not exist here. That automatically is going to mean that the limit does not exist, because in order for a limit to exist, you have to have a left-hand limit and a right-hand limit that agree. The function does have a right-hand limit, so you can have one-sided limits. The limit as x approaches 1 or negative 1 from the right is 1. So there is a left-hand, there is not a left-hand limit, but there is a right-hand limit. So you can have a one-sided limit, but as soon as you don't have one or the other, then that just makes the limit not exist. The rule is that there has to be an approach from the left and the right for there to be a limit, according to the AP Calculus rules. All right, so then we look on the back, and now you notice that there's a piecewise function, which I told you was going to require a left-hand limit and a right-hand limit, but there's no graph. We would like to be able to find our limits without graphing. You could graph it, but if we could avoid that, that would be great. So piecewise function is going to require left hand, right hand, and then the overall conclusive limit statement. So the limit as x approaches 3 from the left. Okay, well, x is less than 3. Think of a number line. So if I'm less than 3, that is going to be able to approach 3 from the left. So I'm going to substitute 3 in here. 2 times 3 minus 4, I get 6 minus 4, so the left-hand limit is 2. The right-hand limit, so I want to be They again think number line to the right of 3, and this would be x is greater than or equal to 3. So there's nowhere to substitute. That limit is just 2. Since the left-hand limit agrees with the right-hand limit, then the limit is 2. For the limit as x approaches 7, so x is less than 7, I would use that as my left-hand limit, and that equals 2. The right-hand limit, I would approach here, this is to the right of 7, and I would substitute the 7 in here. 7 minus 2 is 5. Because the left-hand limit does not equal the right-hand limit, the limit as x approaches 7 for this function does not exist. All right, and then new function, now we're approaching -1. So the limit is x approaches -1 from the left for this function. We want to approach from the left, so x less than -1 would approach -1 from the left, and the left-hand limit is 3. The right-hand limit, x approaches -1 from the right. This would be x is greater than or equal to -1, so I would substitute the -1 in here into this function. So -1 plus 1 is 0, 0 squared is 0, minus 1. So the right-hand limit is -1. Since the left-hand limit does not equal the right-hand limit, this limit does not exist. Okay, so moving on to evaluating limits algebraically. All right, pen's kind of running out. So the first thing you're going to do, we're going to try and find the limit by direct substitution. So give me 1 second. I meant to pull something up and that I could look at. Okay, find it. This one, no. Oh, never mind. Okay, so finding the limit, whoops, there we go. Finding the limit by direct substitution. So do just what it says. Whatever x is approaching, you're just going to substitute it in. Now, you need to answer with the complete limit statement. This is very important. So I have a limit statement here that's just waiting for an answer. If you want to use the printed limit statement and not have to rewrite it, make sure you do your work beneath it so that you can come back here and put your answer here. So I'm going to just substitute 0 in for x, and I get -1. Therefore, the limit as x approaches 0 for the function 2x minus 1 is -1. This pen's running out too. All right, so then same thing, we're just substituting in -3 squared plus 3 times -3. That gives me 9 plus -9. That limit is 0. The limit as x approaches -3 for the function x squared plus 3x is 0. Notice we're not doing a left-hand limit and a right-hand limit. When you, it's not a piecewise function or a graph that you're given, you don't have to have a left-hand limit and a right-hand limit statement. All right, direct substitution. 3 times 1 cubed minus 2 times 1 squared plus 4. So I'm just substituting in 3 times 1 is 3, minus 2 times 1 is 2, 3 minus 2 is 1, 1 plus 4 is 5, so the limit for this cubic function as x approaches 1 is -5. Alright, keep going, substitute in the 3, square root of 4, so here my limit is 2. 2 over -3 plus 2 is 2 over -1, so the limit here is -2. Substitute in 1 here. 1 over 1 squared plus 4 is 1/5. The sine of pi over 2, that's the ordered pair 0, 1. Sine is the y-coordinate, so that is 1. cosine, and you would just do pi times 1 over 3, which is just the cosine of pi over 3. Pi over 3, the ordered pair, is 1/2 comma square root of 3 over 2. Cosine's the x-coordinate, so the limit here is 1/2. Cosine of 3 pi. So on your unit circle, this would be 0 pi, 1 pi, 2 pi, 3 pi. So it would be -1, 0, and my limit is -1. And lastly, the tangent of pi times 3 over 4 is tangent of 3 pi over 4. Second quadrant, that would be -1 over root 2, 1 over root 2. Tangent is y divided by x. So the answer is -1. All right, so the takeaway there is always, 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 always try direct substitution first. Okay. It is worth the couple seconds to try that first, because sometimes you look at something and you just automatically think that you have to do some other method, when all along you just need to plug in the number, and that was going to be a lot easier. Okay, so what if you can't directly substitute? For example, here, if I directly substitute, I get 0 over 0. Well, that's not okay. So when you directly substitute and you get 0 over 0, that's telling you that there's some simplifying that has to happen before you can directly substitute. So, and that's what 0 over 0 is indicating. So I can factor an x out on the bottom, then I can reduce to 1 over x minus 1. Then I can try direct substitution, and I get -1, which is the answer. Let's try that here. If you try and directly substitute, you'll get 0 over 0, 4 minus 4 over 4 squared minus 16. But if you factor the differences squares, you can reduce to 1 over x plus 4. Try direct substitution again, and our answer is 1/8. Here, same thing. If you just go ahead and substitute in 3, you get 0 over 0. So let's try factoring here. We got a difference of squares. Remember, if you have exact opposites, you can cancel them out, but you're going to need to leave a -1 behind. Let's try direct substitution again. We get -1/6. All right, same. If you try direct substitutions, here's what I meant about always try that first. This looks like, oh, of course direct substitution doesn't work. But maybe it does. Like, give it a shot. But it's in this section, so clearly it does not. All right, I'm going to factor x minus 4 times x minus 1 over x minus 4 times x plus 2. I can reduce to x minus 1 over x plus 2. Directly substitute 4 minus 1 over 4 plus 2, which is 3, 6. So my answer is 1/2. All right, algebraic skills needed for piecewise. This should start to look familiar. Factor your sum of cubes. Make sure you know that pattern. Reduce, so I just have x squared minus 2x plus 4. Directly substitute, I have -2 squared minus 2 times -2 plus 4, which is 4, plus 4 plus 4, which is 12. All right, here's where you're going to rationalize the numerator. So I'm going to multiply by the complex conjugate on the top and the bottom. When you FOIL those conjugates on the top, the outer and the inner cancel, so it's just x plus 5 minus 9. Remember to leave the bottom separated into the two factors, because x plus 5 minus 9, that is x minus 4. So this is going to cancel to this. I have 1 over the conjugate. I told you that would happen a lot, but you can't guarantee it's always exactly that. Then I can put in the 4 for x, and I get 1 over the square root of 9, which is 3 plus 3, 1/6. All right, these are similar, so I'm going to skip that in this video. We go back here, and if you directly substitute, then again, you're going to get 0 over 0. So what am I supposed to do here? Although it's not like a situation where you have to rationalize, we're going to use that strategy, and we're going to multiply by the conjugate of the numerator. So on the top, when you FOIL, you get 1 minus sine squared x. Leave the bottom separate. We're going to use our Pythagorean identity to replace 1 minus sine squared x with cosine squared x. That's going to allow us to reduce. And then when you substitute in the pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. 0 divided by anything is 0. The limit is allowed to be 0, so that's not an issue. All right, for this one, so, you know, spoiler alert, the secant of 0 over the tangent of 0 is going to be 0 over 0. Is that true? The secant goes with the cosine, and the cosine, the secant of 0 over the tangent of 0, the cosine of 0 is 1, so the secant is also 1. Tangent of 0 is 0 divided by 1, which is 0. Okay, so this is a different scenario because everywhere else, if you directly substitute, you get 0 over 0. So we also can't divide by 0. That's still a problem, but it's not the same problem. So let's just see how we can maybe simplify this a little bit. Like secant is 1 over cosine, and tangent is sine over cosine. So if we simplify, we just get 1 over sine x, and the sine of 0 is also 0, so that's not helpful. So we're going to have to just stop and say that this limit does not exist. For 21 and 22, those are complex fractions. So you have to simplify the complex fraction. Again, if you just directly substitute, you're going to get 1 minus 1, which is 0 over 0. Okay, so I'm going to get a common denominator so I can subtract on the top, and then I'll be able to divide. So it's going to become 1 over x plus 1 minus x plus 1 over x plus 1 all over x. And then that gives me negative x, 1 minus 1, over x plus 1 divided by x over 1. Okay, so then that's just multiplying by the reciprocal. So if I bring that up, it's times 1 over x. So those are going to cancel. It's going to simplify to negative 1 over x plus 1. Then I'm going to directly substitute the 0. I'm going to get negative 1 over 1, which is negative 1. All right, so if you directly substitute and get 0 over 0, simplify, then try again. All right, last. These are two special limits that you have to memorize. Okay, if you were to graph the function sine x over x, you could see on the graph that the limit as x approaches 0 is 1. Same thing here. If you graph this function, you would be able to see that the limit as x approaches 0 is 0 from the graph. Okay, so you just need to memorize those. Those will allow you to just directly substitute. So if the limit is x approaches 0 and I see 1 minus cosine x over x, I can just replace that with 0. So this would become 3 times 0, and my answer will be 0. Here, I can see the sine x over x. I can replace that with 1, and my answer will be 1/3. Same thing here. It's not exactly what happens, but I can pull out the sine x over x, and it's just going to be 4 times 1 and give you 4. Here, if I have cosine x times sine x over cosine x, all divided by x, that simplifies to sine x over x, so that answer is also 1. All right, and then these last two, if you directly substitute, you get 1 divided by 0. So that's the same problem we had in number 20. If I do that here, I also get something divided by 0. Whenever that happens, if you get 0 over 0, then you have to simplify and then try your substitution again. If you directly substitute and you get a number divided by 0, that's going to mean that the limit does not exist. Okay? It's going to mostly be because of vertical asymptotes. The x values that are restricted down here are 1 and -1. So there would be no limit that existed at x approaching 1 or -1. Here, the vertical asymptote's at -3. That's why the limit does not exist. All right, you can see the filled in notes in Canvas, but I hope this video helped a little.